Good morning, everyone. I'm Sakshi Pareek, a research scholar from the Manipal University, Jaipur. Today, I will be presenting our recent work titled "A Study of Pure and Metal-Oxide Incorporated Polylactic Acid: A Conceptual DFT Approach." This study focuses on understanding how incorporating metal oxides like ZNO and MgO into PLA influences its chemical and physical properties using computational tools. In recent years, PLA has gained a lot of attention due to its eco-friendly nature and potential applications in sustainable packaging and biomedical devices. However, its limitations such as brittleness and low thermal resistance restrict its usability. In this study, we investigated pure PLA and PLA incorporated ZNO and MgO. Using conceptual density functional theory, we optimized the structure and evaluated their structures their electronic, optical, and thermochemical properties. We also calculated HOMO-LUMO gaps, CDFT descriptors, IR and Raman spectra, and other optical parameters using the B3LYP LN2DZ level of theory in Gaussian 16. Polylactic acid or PLA is a biodegradable polymer made of lactic acid monomers. It's derived from renewable sources and serve as a sustainable alternative to conventional petroleum-based plastics because of its low toxicity and good processability. PLA is used in various fields including food packaging, medical implants, textiles, agriculture, and even in the consumer products like 3D printing filaments and disposable containers. Despite these advantages, PLA has interesting drawbacks. It tends to be brittle, show poor thermal resistance, and gas barrier properties. These issues make it unsuitable for application under rigorous conditions, particularly in packaging or biomedical devices that require stronger mechanical properties. This incorporation of metal oxide into the surface of the PLA leads to improved mechanical strength, thermal resistance, and barrier performance. In our work, we selected ZNO and MgO. ZNO is known for its wide band gap and UV shielding while also offering antimicrobial properties. MgO, on the other hand, enhance biocompatibility and provide pH buffering and thermal stability. By incorporating these oxides into the PLA matrix, we aim to improve the structural, electronic, and functional performance. In this study, we used density functional theory, a powerful quantum mechanical approach to analyze molecular systems. All calculations were performed using Gaussian 16 software. We optimized the geometry of PLA, PLA ZNO, and PLA MgO using the B3LYP functional and LAN2DZ basis state. After geometry optimization, we evaluate conceptual density descriptors, homolumo energy, density of states, IR and Raman spectra, thermochemical parameters such as thermal entropy and Gibbs free energy, and optical properties like refractive index and dielectric constant. For geometry optimization, these formulas are used. Here we show the optimized structure of pure PLA and its composite with ZNO and MgO. Each structure exhibits C1 symmetry and singlet spin multiplicity, confirming they are in the ground state. These structures were the basis for all subsequent electronic and optical analysis. To understand the electronic stability, we calculated the HOMO-LUMO energy gap for each molecules. Pure PLA has a gap of 6.710 and PLA MgO shows a slightly reduced gap of 6.66, and PLA Giordano has the lowest gap 6.15. This reduction in energy gap after incorporation of metal oxides indicate enhanced electronic reactivity, particularly in Giordano composite. This diagram shows the distribution of highest occupied and lowest unoccupied molecular orbitals. In PLA, the HOMO is localized mostly around the ester group, while in PLA-Giardino and PLA-MgO, the orbitals extend over the metal oxide regions, indicating improved electron delocalization and better charge transport properties due to metal oxide incorporation. Density of states, DOS. The density of states plot help us visualizing how energy levels are distributed in each system. In pure PLA, the DOS is compact and clustered, indicating high stability and less reactivity. But when Giardino or MgO is incorporated, these peaks become broader and more spread out, showing higher density of available energy state. This confirms that the modified system are more electronically active and may show improved catalytic or sensing behavior. CDFT based descriptors. Now coming to the conceptual density functional descriptors, which offer a deeper understanding of chemical behavior. Ionization energy. PLA Giardino has 7.681 electron volts, slightly lower than PLA MgO and pure PLA, indicating it's more prone to donate electron affinity. PLA Giardino show the highest value at 1.526 electron volt, making it a strong electron acceptor, and PLA Giordano showing the decreasing in chemical hardness, indicating higher reactivity. Electrophilic index is highest for PLA Giordano at 3.3 electron volt, suggesting it the best electrophilic among the three. These value confirming the PLA Giordano has the most reactive electronic structure and is the best suited for application requiring fast reaction transfer such as sensor or antimicrobial surface. Thermochemical properties. We also calculated thermochemical properties such as heat capacity, thermal energy, Gibbs free energy, and entropy. PLA Giordano has the lowest Gibbs free energy, indicating it's the most thermodynamically stable. It also shows the highest entropy at 1.67 167.1 at calorie per mole Kelvin, suggesting more molecular disorder and possibly better thermal motion. These results support the idea that incorporating metal oxide into PLA enhances its thermal properties and stability. These are the optical properties. These figures shows the IR and Raman spectra of pure PLA and its composites. The peak intensities shift upon metal oxide incorporation, confirming structural and vibrational changes. PLA MgO and PLA Giordano exhibit higher peaks intensities and broader vibrational bands, indicating strong dipole activity and improved interaction with incident radiation. Refractive index of PLA, PLA MgO, and PLA Giordano. The refractive index increases upon metal oxide incorporation as PLA Giordano reaches 1.98 in most relation and compared to 1.90 in pure PLA. The dielectric constant also increases. PLA Giordano has a maximum value of 4.935 using the three-party relation, higher than PLA 4.769. In contrast to optical, electronegativity decreased slightly. PLA is 1.798, PLA-MgO is 1.786, and PLA Giordano is 1.650, indicating a shift in electronic structure and potential for greater light interaction. These enhancements support the potential use of PLA composite in optical and electronic devices. Uh, in summary, we successfully modeled pure PLA and its metal oxide incorporated composite using DFT and CDFT approaches. The incorporation of Giordano significantly improved electronic reactivity, UV shielding, and antimicrobial potential. MgO improved thermal stability, biocompatibility, and pH buffering properties. The enhanced optical and thermochemical properties suggest these composites are excellent candidates for sustainable baking, biomedical applications, and optoelectronic devices. These are my references. And I would like to thank Manipal University, Jaipur to provide the necessary research, infrastructure, and support that enabled this work. Thank you for your time and attention. Thank you everyone for listening me. Thank you so much.